Alright, let's solve another example involving spherical symmetry, but this time with numbers. So we will be solving question 43. Let's read the question first. Question 43. A charge of minus 30 microcoulomb is distributed uniformly throughout a spherical volume of radius 10 centimeter. Determine the electric field due to this charge at a distance of 2 centimeter, B 5 centimeter, and C 20 centimeter. So let's have a look. We are going to draw a sphere. So our object is a sphere with a radius uppercase R. Now note we are told that on this object there's a total charge of minus 30 microcoulomb. All right? The radius of this object is 0.1 meter or 10 centimeter. All right? It's always helpful to switch it into meter. Now, one thing I want to highlight is all the formula we derived in the previous example, we're using the volume charge density. And since we are going to create a Gaussian surface inside the object, we need to know the amount of charge inside that object, and therefore we need to know the volume charge density. Luckily, we are given the total charge and we are given the radius, which means we can find the total volume and the total charge. So notice we can find the volume charge density, because it is uniform, by the way, as the total charge divided by the volume of that object. All right? Now note, to find the volume of the object, we need to use the radius of the object. It may sound like common sense, but this is a very common mistake. When we draw the Gaussian surface, we will need to use the lowercase letter r to denote the radius of the smaller Gaussian surface. But when we want to find the volume charge density, we need to use the radius of the object itself, because we are given the charge on the object itself already. All right? Okay, so we calculate the volume charge density, we get minus 0.0716 coulomb divided by meter cube. All right? Let's derive the formula for the electric field inside. Now you will notice we will arrive exactly at the same formula we've seen in the previous example. On the test, when you will need to solve question related to Gauss law, I want to see every step. I don't want anyone to say, hey, this is the formula we derived, let's strictly use the formula. No, I want you to create a Gaussian surface, apply Gauss law, and find the formula from there. All right? Note, it's always the same step to find the formula though. So here we got the electric field. We draw our Gaussian surface, so we want to find the charge inside that surface. Again, it is the volume charge density multiplied by the volume of our Gaussian surface, divided by the area of our Gaussian surface, our Gaussian sphere in this case, multiplied by epsilon 0. We input the value. Again, we can simplify and get back to this formula. It is the same formula we found in the previous example. All right? So volume charge density multiplied by radius divided by 3 epsilon 0. Now for part A and B, we are talking about the distance from the center of 2 centimeter and 5 centimeter. The object is 10 centimeter, which means that in part A and B, we are inside the sphere. So for part A, with r is equal to 0.02, I simply use that formula, but I replace the r with 0.02. I get minus 5.4 multiplied by 10 to the power 6 Newton Coulomb. I do the same logic for part B. All right, so r is equal to 0.05, and the electric field is equal to minus 13.4 multiplied by 10 to the power 6 Newton Coulomb. All right, now for part C, there's two ways to see this. Now, if you are asked on the test, use Gauss law to prove that the electric field outside the sphere is the same as the Coulomb force formula, then you need to do all the step we did in the previous example to prove the formula. But a shorter way to solve that problem is simply to identify that we can replace this object by a point charge at the center once we are outside the sphere. Since we already know the charge on that object, it's minus 30 microcoulomb, we can just use the electric field formula itself. So it's Coulomb constant multiplied by the charge divided by r squared. Or r in this case is 20 centimeter. Note that's really important, and I'm repeating myself here, 20 centimeter is outside the sphere. So that's why now we know if we were to draw a bigger Gaussian surface, we know the total charge inside that surface, we will arrive at exactly the same value. So in this case, electric field is equal to Coulomb constant multiplied by the charge divided by r squared, and we get minus 6.74 multiplied by 10 to the power 6 Newton Coulomb. All right, so all the questions involving spherical symmetry are similar to each other. It might be complex at the beginning, but you will see they all share the same characteristic. It's all the same logic. It's always, when you're calculating the electric field inside the object, it's always about finding what is the charge inside a Gaussian surface, what is the area for a Gaussian surface. The charge might change depending on what value you're given, but the area of a sphere, it's 4 pi r squared. This one does not change. So in the next problem, we're going to be solving question 44. It is a good question regarding cylindrical symmetry. So see you in the next video.